All right, so with these, again, still dealing with vertical asymptotes, horizontal asymptotes. But what we're going to do in this case is we're going to have it so that your numerator is going to be a little bit more complex, a little bit more involved than what we were doing yesterday. So it's going to make things a little bit different as we go through these. Now, in the textbook, when we're going through Math Excel on this one, for everything we're talking about for this one with vertical, horizontal asymptotes, a lot of things they're going to talk about in this case is they're going to call these, when you see this is what we're looking at. This is points of discontinuity. I think that's how you say it. I always say it wrong, but I can't remember how the other way to say it is. But anyway, so if you see that, that's a lot of times when they talk about your vertical asymptotes and your horizontal asymptotes, that in Math Excel, they're going to talk about points of discontinuity. Okay. So vertical asymptotes, still the same thing we were talking about yesterday. It's still where your denominator equals zero. Okay, now if you have something where you can factor something out of the numerator and the denominator, then it's still a point of discontinuity, but they call it a hole because it actually creates a hole in the graph. It's like, if you want to think about it, this would be like having a fence where you've got a gate that you can open up the gate and you can get through it. So a lot of times on this one, so for if we're thinking about the asymptotes as being like fences, that if you have a hole, it's a gate that's in the fence that you can go through it. Sometimes in that case, when they talk about the hole that's here, they will call this also removable. So if they talk about a removable point of discontinuity, then that's basically a hole in the graph. And again, that's going to give you a little gap in the graph that actually lets you cut through your fence to let you get across this thing. Because again, you do need some, occasionally on some fences, you need a gate in there to get through it. So that's basically kind of what we're looking at. So if you've got a hole in the graph, it's like a fence that you can kind of get through this thing. But still, the basic thing is, again, for vertical asymptotes, it's still your denominator equal to zero. That's the big thing. Didn't change from what we're doing yesterday. Here's the part that's going to change, though. And if you look at examples that we have down here at the bottom, notice in your numerators, it's not just 6 over x plus 5 or negative 3 over x plus 5. Now we've got these x's that's involved, some cases x squared. That's going to take up the degree of difficulty a little bit. So now when we're looking at these, we got to kind of go one extra level for this one, is that when we talk about horizontal asymptotes, it's based on the degree of your numerator and your denominator. So the degree of the numerator, we're just going to call that m. The degree of the denominator is going to be n. And so if we start checking these out, if the degree of the numerator is less than the degree of the denominator, then there's a default back at y equals 0. So that's going to take us back to like, this problem where we had, we're graphing this and we had vertical asymptotes and horizontal asymptotes, both of them at 0. So we had something like that. So this would kind of be there. Okay, if the two powers are equal, if you've got x squared over x squared, if we're doing something like that, then basically the powers cancel each other out, and all you're left with is your coefficients. So it's the term, whatever your y term is, or the m term of the denominator and the numerator, you kind of put those two things together and you simplify that number, and that's going to tell you what it's going to be. All right, and then number 3, this is the one I hope you get. That again, you'll probably get some of these as we go through this one. If the numerator is greater than the denominator, you don't have a horizontal asymptote. It's a slant asymptote, but we're not gonna worry about graphing the slant asymptote. That part they'll show you in pre-cal, and that's the part where they're gonna, again, they go one extra step on that one because for us, we're just gonna say we're not gonna worry about it. When you get into pre-cal, basically what you're gonna do is you're gonna do synthetic division to find out what the line is, the equation of the line, and then you graph that line, and that becomes your slant asymptote. But again, today we're just making sure that we've kind of got it as we go through these. But we'll kind of figure it out as we go along here. Okay, so here we go. So number 1. So we're going to find the vertical, horizontal asymptotes if any exist, and then we'll do a quick sketch a little bit later on. Right now, we're just going to make sure we've got these, and then we'll actually sketch some here in a little bit and actually get some graphs of these. We'll do this on the back side. But right now, we're just making sure everybody's okay finding vertical, horizontal asymptotes. Okay, so over here. So for vertical asymptotes, again, it's denominator equal to 0. So that's x minus 5 equals 0. Really easy on that one. That's x equals 5. Okay. Now for horizontal, here's where the work comes in. Because now for the horizontal, this is where we're looking at this part. For this part of what we're doing for this one, the numerator is degree 1. Denominator, because it's x to the first power, x to the first power. Also degree 1 for the denominator. So in this case, they're both 1. So that means in that case, the m would equal n. So our horizontal asymptote is basically we're going to take the first two numbers we've got here, and we're going to cancel out the x's. If you cancel out the x's, that leaves you with -2. There you go. So there's your y. There's your asymptote at -2.
Is that for every problem?
If the powers are the same, yes. And we'll show you the other one here in just a second.
Oh, like if it's x, if it's both x are to the same value.
Right. So, and we'll show you what happens if they're a little different power on the next one. Question.
So why m is 1 and the n is 1 is because there's no power. Well, one is
Understood power. Yeah.
Okay.
Yeah, and it's actually, and again, in that case, you just cancel out the x's, and whatever you've got left over for those leading terms, that's going to be your horizontal asymptote. Which again, is not too bad. Okay. The only thing we've got back here, some of these they may ask, is this vertical asymptote removable? And for that part of it, the only thing you could do back here is you could factor out a -2. And the only way that this thing would be removable, oh, sorry, can't see that. The only way that this thing would be removable is if you could cancel something out over here. We're not able to cancel, so this thing is not removable. Okay, so number 2, again, pretty much same thing for this one. We're going to take the denominator. We're going to set it equal to 0. And this kind of happened on the last test we had. I think the last problem on there, we snuck in the factoring problem on you after you plug some stuff in and work some stuff out. So this one, same thing here. You got to find the factors of -12 that equal 1. Should be 4 and 3, right? Again, B term is positive, so the bigger number is positive, which means the smaller number is going to be negative. If we set both of these equal to 0, we get x equals -4, and we get x equals 3. Okay, and they will ask you, are either one of these two vertical asymptotes, are either one of these two removable? And if you check for this one, we had x minus 3 over, when we factored the bottom part off, that was basically what we had here, right? So if we factor this thing out, this was x plus 4 and x minus 3. And these two things cancel, right? You got x over 3 over x over 3. So where these two things cancel, again, that gives you a gap. That's the break in the fence that we have. So that's a gate we've got that we can get through in this thing. So that's the part that we can jump from one side to the other. So for this one, x equals 4 is actually a vertical asymptote. X equals 3 is actually going to be a hole in the graph. So this would be a hole that's going to be there. Or again, depending on which book you use, which part you talk about, some places the book will talk about being a hole. But Math Excel talks about being a removable point of discontinuity. It's still the same thing. It's just they're just calling it something. Hole's a lot easier to say than removable point of discontinuity, but that's what Math Excel is going to call it there. So x equals 4 is actually our only vertical asymptote. X equals 3 is a hole that we'll have in the graph. Or again, think about it like being in a fence, and we've got a gate that's in the fence that we get to get through there. So. All right, and then horizontal asymptote. Numerator is degree 1. Denominator is degree 2. And when you do these, you always compare m and n. M is always going to be first because it's alphabetical order. So if we're talking about m and n, if we've got 1 and 2, 1 is less than 2, right? So m is less than n. And this one's actually kind of good because if the m value is less than the n value, then we've got a horizontal asymptote at y equals 0. So we don't actually have to do any math other than just comparing the two numbers. So for this one, we've got a horizontal asymptote at y equals 0. Because
how many?
yeah, looking at your powers over here.
Okay.
Yeah, so we've got x to the first and then
So
x
that's
squared.
1, and then it's 2.
Yep.
Oh, okay. So you don't have to count how many x's there are. You just count how many
Nope,
powers
just
there are.
counting your highest power. Yep.
Why can't that be like n to be the numerator?
I don't know. It would make more sense that way.
It makes so
Yeah.
much more sense.
But I'm guessing it's probably the original language it came from and how they used it. It was probably, the different words they used there.
I know I'm gonna accidentally put n as the numerator.
Yeah. I may be nice and let you have that reminder on the board that m is the numerator and n is the denominator. All right. Okay. So number 3. So if we factor the bottom part, we've got x minus 4. So vertical asymptote, just x minus 4 equals 0. That's x equals 4. And again, the check is we want to see if it would be removable, if we could cancel anything out. And this was one, hopefully you can look at it and kind of go, well, okay, if I factor this thing off, is there any way we're going to get x minus 4 out of the top part up here? No. Yeah, it's just, if it was a 4 at the end, maybe 8 something. But in this case, with that last number being 3, the only factors of 3 are 1 and 3. There's no way we're going to get anything that's going to cancel. So there is nothing that cancels. So that's just our vertical asymptote. No holes, nothing removable, nothing we got to worry about there. Okay, for the horizontal asymptote, need the 2 degrees. Oh, you think about it this way. If you stack them up, m comes before n, so m is on top, n's on bottom. So you can think m over n. Maybe. That might help. Maybe. Don't know. No? All right, so numerator on top is 2. Bottom is 1. So in that case, your m is greater than n because 2 is greater than 1. And that one's also kind of nice because if the m value is greater than n, there is no horizontal asymptote. We're not going to worry about that one at all. So that one, the answer would just be that there is none.
So we only have to worry about doing actual math for the horizontal asymptote when they're equal?
Yep. Okay. And then you're just simplifying the little fractions you got there.
Okay.
Yep. And again, there's no horizontal asymptote. It actually turns into a slant asymptote. And that's where you'd have to do synthetic. And again, just kind of giving you an idea. This is where you would do synthetic division with this problem. And whatever the answer is that's left over, it's going to give you a line. And that line would be what would, in place of the horizontal asymptote, it would be a slant asymptote. But we're not, again, that's something we'll save for pre-cal, for those of you going into pre-cal. Okay, vertical asymptote for number 5. We got x squared plus 5x equals 0. All right, a little different factoring on this one. They both have an x, so let's take the x out. So it gives us x times x plus 5 equals 0. Hopefully everybody's okay solving from here. So actually we're going to get 2 in this case. We're going to get 1 at x equals 0. We get another one at x equals -5. So this one's got 2 vertical asymptotes, which is okay. Sometimes that's going to happen. Okay, horizontal asymptote. Numerator m over n. Numerator has degree 1. Denominator has degree 2. And since m is less than n, can't see it there. 1 is less than 2. It's always got to be m and n first. Let's go through that one. Since m is less than n, again, that default goes back to number 1 up here. So if m is less than n, it defaults back to y equals 0. All All right, everybody okay? So far, so good. Okay. All right. So now we're gonna. If you want to flip over on the back, you can. If you want to go to a separate piece of paper, you can. Just for me to keep my lines straight, I'm gonna go to a separate piece of paper. I don't. Whichever way you go on this one, I don't care. If you want to go back, that's fine. If you go a separate piece of paper, that's good too. All right. So for this one, we're gonna find the horizontal vertical asymptotes, and then after we do that, we're actually gonna sketch the graph. So. Okay. And again, notice it doesn't say plot. Every time you get these, it says sketch. It's not. It doesn't have to be perfect. It just needs to be in the ballpark. Okay. So vertical asymptotes. Again, that's denominator equal to 0. Math really easy there. That's just x equals 5. All right, nothing you can do to factor these, correct? So we don't have to worry about any holes because there's no way that this is going to factor and cancel. So this one, there is no hole. There's no removable point that we're going to have from this thing. Horizontal asymptote should go pretty easy here because the numerator is degree 1. Denominator also degree 1. So the m value, the numerator, denominator both have same degree 1. So in that case, you can just look at the x values that you have and just cancel out those x's. This one we're also left with just a 2. So horizontal asymptote y equals 2. Question?
Is that when they equal each other? Is that all we're really gonna do?
Mhm.
Just cancel. Okay.
Yep. Yeah. So if yeah, so yeah, whenever you if the numerator denominator degrees are equal, basically you can take everything past the x's past and you can just cover that up. And there you go. There's your answer right there. Just y equals 2.
So
You know.
the hardest thing is really the vertical asymptote.
Yeah. And if that had been 2 over 4, just let me see if I can pencil that in real quick. If that had been 2 over 4, like that, you cover up everything back here, you would just simplify that and make it a half, and then you're good to go. Or if that had been 12x plus 3 over 4, cover up everything back here, that's 12 over 4, it's just y equals 3. So yeah, so if they're equal, it's really just that easy that you just get rid of everything from the x's past, and whatever number you're left with, that's your answer. That's all it is. And then again, you may have to simplify it just a little bit based on what you got there. All right, so when you graph it, and again, we know we're going to go to 5 and put a vertical asymptote. We're going to go to 2 and put a horizontal asymptote. So that means this graph needs to kind of go, way over this way. Okay, so here we go. So jump back in. So again, we're going over 5. 1, 2, 3, 4, 5. And we're just going to go up 2, just a normal 2. So instead of the asymptotes being here, asymptotes are going to be centered at that point at 5, 2. So we got x equals 5, y equals 2. So that's the center of our graph now. And that's where our asymptotes are going to be. Okay, so there's our fences that we're looking for. Okay, now here's where we go back. Here's where we got to add in something new. Here's the big jump on this one because we've got x's involved. You've got x's in the top. Now, obviously, we had the x in the bottom. But if you plug in a negative number, that's going to make the top number. If you plug in like -4, that's going to make the top number negative, correct? If you plug in 5, the top number is positive. So depending on what number you plug in, the answer could be positive, the answer could be negative. So for these, yeah, we don't really know if it goes here and here or here and here. So what we're going to have to do, and this is the new part we got to add in for this one, because we don't really know where the numbers are going to be. So here's the new thing we're going to have to do. So to find out where the graph goes, we're going to have to plug in a value. Fancy math word is evaluate. Ooh, there we go. So plug in. That's evaluate is the fancy word for plug in. You know, a value of x on both sides of the vertical asymptote. Okay. And for that one, we know, I'm going to slide it up just a little bit. We know our vertical asymptote is x equals 5. So all we've got to do is plug in a value that's on either side of x equals 5. Well, so we're going to make it easy. If we're going to plug in a number to the right and left of x equals 5, we're going to plug in x equals 6, and we're going to plug in x equals 4. Because if 5 is here, we need to plug in 4 and see what happens. We're also going to plug in 6 and see what happens. And then where those points are, because if we plug in x equals 4, the point's either going to be up here somewhere or down here, and that's going to tell you which part of the graph you're going to shade. If the point's up here, it's in here. If the point's down here, you're going to shade this part. Same thing for x equals 6. You plug it in. If that point happens to be down here somewhere, you know you're here. If it's up here, then you know you're in here. And the difference on this one is when we're doing these with the x's on the top and the bottom, it may not always be that it's going to be here and here. It could be that it might possibly be that they're both on top, or it could be that they're both down here. So we could have a graph that looks like this and this at the same time. That's the possibility of the answer being there. Now, most of the time, it's still going to wind up being like this, where it's either here and here, or it's here and here. And that part we don't know really until we go back and plug in the numbers. Okay, so we're going to do that on the side over here. We're going to plug in x equals 4. Again, evaluate is the big fancy word, so we're going to plug in 4 back into the original equation. So that means we get y equals 2 times 4 plus 3 over 4 minus 5. All right, so that is 8 plus 3 over negative 1. That's 11 over negative 1, so that is negative 11. So if we plug in 4, the order pair is going to be at 4, negative 11, so that's going to be way down here somewhere. And that's all we need is we just need to know if it's above and again, you got to think about these as being fences. Either it's in this side of the fence or it's on that side of the fence. So that graph will look something like that. Okay, now again, 90% of the problems we're doing now once we get into pre-cal, it changes a little bit that it's more, it could be anywhere, any point, any time. But most of the graphs we're doing now, I'd say 90% of them, you can pretty much always bet that if this one's here, the other one's going to be here. But sometimes they're not. So this is one we got to be careful just to see what happens. So now we'll plug in x equals 6 and see where that point is, see if it's up here above or if it's down here below that side of the fence. So if we plug in 6, we got y equals 2 times 6 plus 3 over 6 minus 5. Again, just taking that 6, plugging it back in here. That gives us 12 plus 3, that's 15 over 1. So that y value is just at 15. So if we plug in 6, we get 15. So we're going to go to 6, 15, which puts us way up here somewhere. And again, that keeps us in this part of the fence. So that means when we get down here, we'll have something like that. Okay, now, and again, if you're in a hurry, for some reason, don't know why you would be, but if you plot the first point and you get it down here, there's a really, 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 really good chance the other one's going to be in the opposite corner up here. Again, occasionally they'll sneak one in where they're both here and here, but most of the time, if there's only one vertical asymptote here, Usually they're going to be in opposite corners. Occasionally they may sneak one in and put one there and there, but most of the time they're going to be here and here. Question?
So you use 4 and 6 because they're on both sides of 5?
Yes.
Okay.
So whatever your vertical asymptote is, you pick one number to the right, one number to the left, and that way it lets you know what happens when you get close to this graph.
Okay, that's what I was
Okay.
like.
Why we pick those numbers? Okay.
Yeah, why you pick 4 and 6? Because I mean, 4 was another.
Yeah. So wherever your vertical asymptote is, if it's at 5, you want to pick on just on either side of it to know what it's doing when you get there. Okay, so here's another one. Now, this is one kind of like the last question. Somebody said on this last example, where was it? Back here on number 4, we had 2 vertical asymptotes. We'll show you what happens when you graph one with 2 vertical asymptotes. I think this may be the last one that we'll do, because if we do this one, I think this will be enough to kind of wear everybody out, and we'll wrap it up after this. After this one, yeah, this is the last one we'll do for today. All right, so let's actually go back and do that 4th example we had. I'm going to change it to, instead of x minus 6, we'll do x minus 2. But it's basically the exact same graph as this one. Just change that one number here so we can kind of see what's going on with it. Okay, so with vertical asymptotes, again, just taking the denominator, set it equal to 0. We can factor out the 1x from both of those. Leaves us with x equals 0, x equals negative 5.
So you put x minus 5 equals 0.
Yeah, because we had x plus 5 equal to 0. So if we set that equal, if we do x plus 5 equal to 0, yeah, then we get x equals negative 5. Thank you for that one. That's a good catch.
I have a question.
Sure. Okay, horizontal asymptotes. And again, if you go m and n, because it's numerator, denominator, if we go that part, numerator is degree 1, denominator is degree 2. So m is less than n. Because again, 1's less than 2. And that one, if that's the case, if m is less than n, we don't have to do any math at all, which means the horizontal asymptote doesn't move, it stays at 0, which is kind of nice in that way. We don't have to move this thing around anymore. Okay, so drawing the asymptotes. This is where again, this is the part that's kind of easy, just drawing the asymptotes. We've got this line. We've got that. So there's our XY axis. And if we go with the asymptotes, I'm going to put those in red just so they stand out really, really. How about we go orange? So we got a vertical asymptote at x equals 0. We also have another one at negative 5. 1, 2, 3, 4, 5. And then we had a horizontal asymptote right on top of the axis at y equals 0. So we got one going this way. Okay, so again, there's our vertical asymptote at x equals 0. There's our other vertical asymptote at x equals negative 5 right there. And then our horizontal asymptote would be here. That's at y equals 0. And should have had this thing shifted over a little bit because I left way too much room over here. But anyway, it's all right. All right, is that okay where we have our asymptotes?
Yeah.
Okay. Now, because we've got 2 different sets of asymptotes here, one at 0, one at negative 5. That means that we have to, again, we're going to plug in a number around negative 5. So we're going to plug in negative 6. And we're also going to plug in negative 4. Because we need to know what's going to happen over here. We also need to know what's going to happen over here. All right, and this is the part that's not hard. It's just kind of tedious because we just got to keep plugging stuff in. So we're going to plug in x equals -6, or again, the fancy math word of the day is we're going to evaluate -6 back into the function up here. So it makes it -6 minus 2 over -6 squared plus 5 times -6. All right, so that gives us -8 over 36 minus 30, which is -8 over 6, which is about, yeah, -1.3. Yeah, if you're not sure of your math skills, that's where you can always check your calculator. But that's basically, you know, if you change it back to a mixed number, that's 1 2/6, which is 1 1/3. 1/3's, basically about 0.3. Okay, so our order pair there is at -6, -1.3. We just need to plot that one to see if we're above the line or if we're below the line. With it being -6, -1, we're definitely below the line, so that's going to put us in there. Which means that graph will stay somewhere in here, something like that. Okay, and again, if we didn't have this one over here, you could probably take a really good guess and think that the other one's going to be up here. Now, with the extra one that's here, here's kind of the good news. If there are no holes in the graph, so again, we've got this fence that's here. If you think about these being fences, if there's no holes in these fences, there's no gates. Once you're in here, you're stuck in here. So if we know that we plot in -4, let's just go ahead and figure out where -4 is going to be. So we're going to plot -4. So it's going to be y equals -4 minus 2 over -4 squared plus 5 times -4. All right, so that gives us -6 over.
You ever been in decimal form and fractions?
Yeah, just so you can kind of know, because it's easier to graph decimals than it is to graph fractions to me. I mean, either one's fine. Doesn't really matter which one you get there. -4 squared is 16. 5 times -4 is -20. That's -6 over -4. Two negatives cancel. That means it's 6 over 4, which means that is 1.5. Okay. Again, it's not hard. It's a little tedious because you got to plug in numbers, you got to evaluate, you got to work it through, you got to do all the order of operation stuff. If you have the good Casio calculators, you're at advantage because you can take it and kind of plug this thing in. If you've got the Texas Instrument, you might have to do it in 2 parts, but you can still get the answer there. So. Oh, it's not. Sorry. Yeah, sorry. I got happy with my negatives. It's just -4 and 1.5. Thank you. A little correction take there. I don't know what you're talking about. There's no negative there. I don't know what negative you're talking about. Okay. All right, so -4, 1.5 would put you up here, right? So that means this graph is going to do something like this. Now, when you get towards the bottom, there's not a fence, there's not a gate, there's no hole here, and that's where the holes would come in handy. If you had a hole here, you could actually go through this and come back over here. But since there's no hole, once you get over here, you have to turn and then go back this way.
Do I have to draw it all the way out?
Yeah.
Then why don't I draw the bottom one all the way out?
Well, because this one, there's the fence goes forever this way, so you just keep going along the edge of the fence. This one, once you're here, the fence stops and it goes this way. So once you get down here and you get the corner, you gotta keep moving. So then instead of getting stuck in the corner, you're just gonna move and go that way. Okay. Right.
Never mind.
Okay. Answer your own question.
Yeah.
Okay, that's good. All right. So good news is if you don't have a hole in the graph, and you're up here, you're always going to stay in here. If that point had been down here, you would always stay down here. So we don't actually have to plug in -1 over here. But if you plugged in -1, it should be somewhere along in here. But again, we don't have to do that because there's no hole in here, which means you cannot cut through. If you had a hole in the graph, you can actually cut through and get to the other side because that would be like a gate. Okay, so we'll only need one more point over here. X equals 1 to figure out if we're up here or down here, and then we'll just kind of adjust from there. Okay, so last point. I mean, we can keep doing more points if you want to. Okay, just make sure. All right, so we plug in X equals 1. We've got Y equals 1 minus 2 over 1 squared plus 5 times 1. All right, so that is -1 over 1 plus 5, so that is -1 over 6. Okay, it's not a very big negative number, but it's like 0.16. But again, the main thing on that is it's negative. So if we go to graph this point, it's not up here, it is down here, which means that part of the graph has to be something like that. And again, there's no holes, so once that point puts you in here, you have to stay in this part of the fence that's in here. If we'd had a hole here, then yeah, we could have gone through here and cut over and wind up going this way. But usually your holes will be somewhere here in the middle. I don't think you ever get a hole out on the end. Now there may be some weird cases if you go way on past some other stuff, but pretty much everything in pre-cal, when you go there, your holes will be somewhere in the middle. So it would come through here, you would cross over and then come down this way or something like that.
So if you're on